One of the important algorithm, B-tree. B-trees are balanced search trees designed to work well on magnetic disks or other direct access secondary storage devices. B-tree nodes may have many children from a handful to thousands. That is called the branching factor of a B-tree. Every n node B-tree has height order of log n. Therefore, B-tree can be used to implement many dynamic set operations in time order of log n. B-tree generalize binary search trees in a natural manner. If a B-tree node X contains n of x keys, then X has n of x plus 1 children. The keys in node X are used as dividing points separating the range of keys handled by X into n of x plus 1, each handled by one child of X. When we are searching for a key in a B tree, we make an n of x plus 1 weight decisions based on comparisons with the n of x. Always the number of decisions based upon number of keys presented in B tree. Here M is a root and D and H are children. D, H, Q, T, X are the children of M. B, C, F, G, J, K, L are children of T, H. N, P, R, S, V, W, Y, Z are children of Q, T, X. Definition of a B tree. A B tree T is a rooted tree having the following properties. Every node X has the following fields: n of x, the number of keys currently stored in node X, the n of x keys themselves stored in non-decreasing order, which is key 1 of x less than or equal to key 2 of x less than or equal to key 3 of x, so on till key n of x x. Leaf of x. It is a boolean value that is true if the x is a leaf and false if it is an internal node. If x is an internal node, it contains n of x plus 1 pointers. Hence, C1x, C2x, so on, Cn of x, x are children. Leaf nodes have no children, so their C1 fields are undefined. The keys key I of x separate the ranges of keys stored in each subtree. If ki is any key stored in the subtree with root ci of x, then k1 less than or equal to key1 of x less than or equal to k2 less than or equal to key2 of x less than or equal to so on up to key n of x x less than or equal to key of k of n of x plus 1. Every leaf has the same depth, which is the tree height h. There are lower and upper bounds on the number of keys a node can contain. These bounds can be expressed in terms of a fixed integer, t greater than or equal to 2, called the minimum degree of the B tree. T greater than or equal to is the minimum degree of B tree. Every node other than the root must have at least t minus 1 keys. Every internal node other than the root thus has at least t children. If the tree is non-empty, the root must have at least one key. Every node can contain at most 2t minus 1 keys. Therefore, an internal node can have at most 2t children. We can say that a node is full if it contains exactly 2t minus 1 keys. Basic operations on B-tree. In basic operations, we present the details of the operations B-tree search and B-tree create and B-tree insert. In these procedures, we adopt two conventions. The root of the B tree is always in main memory so that disk read on the root is never required. A disk write of the root is required, however, the root node is changed. Any nodes that are passed as parameters must already have had a disk read operations performed on them. Let's look into the procedures. Searching a B tree. B-tree search is a straightforward generalization of the tree search procedure. B-tree search takes as input a pointer to the root node X of a subtree and a key K. So X is the root, X, X is the root node of a subtree and key K to be searched for in that subtree. The top level call is thus of the form B-tree search, root of t, k. If k is in the B-tree, B-tree search returns the ordered pair y of I, consisting of a node y and an index I such that key I of y equals to k. Otherwise, nothing is returned. Here, in the B-tree search procedure for binary search trees, the node encountered during the recursion from a path downward from the root of the tree, which is, let's take I as a value 1 and let's do the recursion towards the downward from the root of the tree. The number of disk pages accessed by B-tree search is therefore theta of h equals to theta of log t n. So the number of disk pages accessed by B-tree search is therefore theta of h equals to theta of log n, where h is the height of the B-tree and n is the number of keys in a B-tree. Since n of x less than 2t, the time taken by the while loop of lines 2 to 3, which in each node is order of t, and the total CPU time is order of th equals to order of t log n. Creating an empty B tree. To build a B tree T, we first use B tree create to create an empty node and then call the B tree insert to add new keys. Both of these procedures use an auxiliary procedure, allocate node, which allocates one disk page to be used as a new node in order of one time. We can assume that a node created by allocate node requires no disk read since there is as yet no useful information stored on the disk. So B-tree create of T B-tree create requires order of 1 disk operations and order of 1 CPU time. Here you can look at the algorithm for B-tree create.